Okay, so we've come a long way, and I just want to review what we've learned so far and possible future videos that I might make after this list. So I want to make a review list of things that we've looked at. We started with linear regression. Then we went to logistic regression. And this was a classification problem. We made the difference between okay. So we found the difference or defined the difference between regression and classification and defined the tasks that we would use linear regression for and logistic regression or classification for. Then we extended that to neural networks. And this whole idea that you can sort of plug and play you can plug and play logistic regression over and over and over again in order to create a neural network. If we sort of have just neural networks, a neural network is sort of just a bunch of stacked logistic regression layers. And then after that, we went more into the derivation behind gradient descent. Where we not only, so in the first part, we sort of found out how do you compute your prediction, and then we found out later how do you actually find out the parameters for that. How do you find out W, right? You guess initially, and then you find out ways to improve your guess. And you can do that for linear regression, logistic regression, and then there are more complicated ways called backpropagation for neural networks in general, right? But it all stems from this idea of guessing and checking, I guess. And that's gradient descent. And then we talked about some subtleties in terms of the value of alpha. And we after that we went into more important stuff like vectorization. And this was more for treating your data set as a data set as opposed to just individual examples, right? Storing things in tables and matrices, and how do you compute the hypothesis function for a neural network, computing multiple outputs at once? How would you do that all in matrix form? And the advantage of that being that you can run computations in parallel, speed up your training process, and other things like that. Now, there's vectorization, and then possible further things to learn about. I might make videos on this, I might not. Are these things called atom optimization, atom optimization, and that consists of two things, which is momentum and eta grad, or no, sorry, not eta grad, RMS. So these are just key terms for you to search up. These have nothing to do with what we've done so far, but atom optimization is, so gradient descent, what we described right now is sort of just gradient descent in general, but there are other more specific types of gradient descent, one of which is atom optimization, which is the one that's usually used in machine learning or in deep learning practices. And that seems to be better than just normal gradient descent. It's sort of just gradient descent, but with a couple of modifications on top of that. One of them being momentum and one of them being RMS prop. If you fuse those two methods together, then you get atom optimization. And so I haven't explained what any of that means, but these are kind of key terms if you want to search them up and learn more about those. And so we also covered, what it means to do hyperparameter tuning. But there is a very rich field of research around hyperparameter tuning that we haven't gotten into yet. We sort of just literally scratched the surface of that. But now you should have a better idea of what machine learning is, what deep learning is, and how to go about this from now. So thank you for watching.